Hi everyone, and welcome to this lesson on volumes of solids of revolution, the washer method. This is the counterpart to the disk method. Think of a disk, but with a hole in it. So when we say washer, we mean like the hardware kind of washer, or if you prefer food analogies, think of a lifesaver or a donut. That's the type of washer we're talking about. So let me take you to a couple of applets first to give you more of a visualization to set the stage for what it is we're talking about. So this first one is from mathdemos.org. If you take a look at the animation there, you can see that the washer is forming. It definitely looks like a disc, but it has that big hole in the middle of it. So what we're going to have to do is come up with a formula to account for the hole being there, because we don't want to include the area of the hole when we're finding our formula that we're going to use. Once again, we're going to be using the idea that was built upon Riemann sums and using the rectangles underneath a curve. And here, once again, we're going to have representative rectangles that we will think of rotating that representative rectangle about an axis of revolution, and that's what's going to create our washer. If you go to this website, I purposely left the URL there for you at the top in case you wanted to investigate it on your own. If you scroll down, they have a lot more other pictures and demonstrations of the types of things we're talking about. There's our hardware washers right there. There's your good old lifesaver. And the donut. Or I guess you could use a bagel too, right? So they give a lot of different visualizations. You can even think of like a DVD or a CD type of disc that has the hole in the middle there. So this is a great website if you care to explore it later on. Let me take you to another visualization. This is from calculusaplets.com, and if you take a look at it, you can see the rough outline of what looks to be a cylinder, but there is a hole going down the cylinder there. So imagine taking this yellow region and rotating it around this black, the x-axis right here, going through the middle. All right, so what you can see here is the representative rectangle that we'll be talking about in our lesson today, that dark gray part. And imagine flipping that around the x-axis, and that's going to create the gray washer that you see here. All right, so that's what we're going to have to come up with a formula for, as that's going to become our integrand for our definite integral. So let's go back to our lesson. So if we think once again of how in general we get volume of anything, remember it's going to be the area of the base times the height, the thickness. So just like we did before, our volume calculations are going to be doing a definite integral of the area of, in this case, the washer face times the thickness, dx. If it's in terms of a different orientation of our representative rectangle, that integrand is going to be in terms of y. So very similar to what we saw with disks. As a reminder, again, a solid of revolution is a solid generated by revolving a region about a line, which we refer to as the axis of revolution. The solids we're typically going to be dealing with will involve a region bounded by a curve, the x-axis and or the y-axis, and perhaps some horizontal or vertical line. What we need to do is find the volume of the solid disk and take away from that the volume of the hole. So let's try to replicate that gray washer we saw on that last applet from calculusaplets.com. So here's the outer edge of our washer, and here's the hole in the middle. Basically what we want is just this part. So we need to figure out how to do that. And again, we're going to build upon the fact that volume of anything is generally the area of the base, so we need that area of that shaded region I just shaded in for you, times the thickness. All right, well, it's a circle, so we know pi r squared. So if we thought of big R as being the radius to the outside circle, so that's big R, and little r as the radius of the hole, we could come up with an expression for the area of the entire outside circle and then subtract from that the area of the inside circle. So that would look like pi big R squared minus pi little r squared. Now, that's just the area of the face of the surface. Remember, to get volume, we need to multiply this by the height, the thickness, which we're typically going to refer to as either dx or dy. And we're going to turn it into a definite integral. All right, so typically what we're going to use, notice you can factor out a pi here. So the basic formula we're generally going to use is pi times the quantity, big R squared minus little r squared, and then either dx or dy, depending upon the orientation of our representative rectangle. So let's talk first about solids that are revolved about a horizontal axis. When we revolve about a horizontal axis, I have a picture for you on the next slide. It looks like this. We end up with a vertical representative rectangle. So your representative rectangle would maybe go something like this. All right, so that would be a dx because the orientation of our representative rectangle is vertical. That turns it into a dx problem. So let me scoot back for a second. The outer radius, capital R, is the distance from the axis of revolution to the far side of the curve, of the rectangle, which you'll see here, capital R. So it's going from the axis of revolution, which in this case is the dotted line there, to the far side of your rectangle. The inner radius R is the distance from the axis of revolution to the close side of the curve, or the close side of your representative rectangle. All right, so you'll notice little r here going from the dotted line, again your axis of revolution, to this closest side of the representative rectangle. Then you can see how you set up your volume integral. Again, your limits of integration need to be x values because it's a dx problem. Now, if we have a vertical axis of revolution, that's going to turn it into a horizontal representative rectangle. So it would be going something like this. And that turns it into a dy problem. So capital R is once again the outer radius, the distance from the axis of revolution to the far side of the curve. So once again, from the dotted line, which is your axis of revolution, to the far side of your representative rectangle. Little r is the inner radius, that is the distance from the axis of revolution to the close side of the curve, or representative rectangle. Again, little r is really the radius of the hole itself. So you can see how the volume integral gets set up. If it's a dy problem, your limits of integration need to be y values, but still you have that pi times big R squared minus little r squared. You do just need to remember that your integrand here needs to be in terms of y. Now I want to point out to you two major characteristics of a washer method problem. And think of this picture and this one. Notice in both cases your representative rectangle is perpendicular to the axis of revolution, but it is not touching it. That is contrast to the disk method, which the representative rectangles were still perpendicular to your axis of revolution, but with a disk method, those rectangles were touching the axis of revolution. In a washer method, they are not. So that is really those two characteristics, being perpendicular to your axis of revolution, and then whether it touches the axis or not. That's really what differentiates a disk method problem from being a washer method problem. As you go about finding your capital R and lowercase r, you're still going to adhere to that top minus bottom and right minus left ideas. So as you work through practice problems, keep that in mind, that as you find your expressions for capital R and little r, you're always doing top minus bottom or right minus left.